Hello again. In this video, we are going to tackle the basic register functionality, creating the fundamental connections needed for a register. Now, this does not include any of the other stuff that we want to be able to do with a register. It's just the basic fundamental functionality. And to make sure that things are working properly, we create a bus testing harness so that we can test inputs into this register. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. So let's get into this register build. Now, full disclosure, I recorded this once. I didn't like the flow. It wasn't going to work out the way I wanted it to, so I deleted that, popped everything off the breadboard, and I'm starting again. It kind of means that I have a bit of a head start on where I think I want to place these. So, as I said before, I don't typically pre-build any of these. You're seeing it built for the first time on camera. Well, in this case, I have built it and I didn't like it, and it was that I didn't like the build, I didn't like the recording. Anyway, I have two breadboards here. I've taken one of the power rails out so that I can connect them together, and I'm going to work off two breadboards today. I will likely end up adding more because I need additional bus outputs, so I will work on that. First thing I'm going to do is tie power and ground together so that I don't make any silly mistakes there. And whether these end up on this side or on this side or both, I actually won't know until I get closer to the end of the build. Now, a register. A register's primary purpose is to hold data, and I've got a 16-bit computer. I'm going to be using 16-bit registers, and my intent was to use 74 LS 574s. Well, they weren't available, so I ended up purchasing these 74 HCT 574s. They are TTL compatible to the 74 LS series, but they are high-speed CMOS, not the transistor. I believe they're NPN type transistors, but I don't know for sure. Don't quote me on that. So, placement here. I'm going to stick these right about here to get started. And as I said, these are just marginally faster. I've got to roll these pins in just a little bit, even though I had them in a breadboard before. They seem to be a little stubborn this morning. Okay, I'll stick that there and stick that there. All right, perfect. Now these need power and ground. I've pre-cut a couple of those wires to make this assembly go a little bit easier. Ground is on pin 10, pin 10. And I did not get this one lined up well, so I'm going to put that at an angle. And I'm okay with that. And power up here on top is on pin 20. So it's a 20 pin package. That is not pin 20. That's pin 20. Let me switch over to the wiring diagram. Okay. So there are two control lines that we want to be interested in. One is a clock pulse, which indicates when we are going to latch that data that sits on pin 11 here. Actually, I'm going to move it closer to the IC. And then I've got an output enable, and those I'm just going to directly tie low. The output enable is on pin 1. These will always be outputting. And the reason they're always going to be outputting is because I'm going to actually use line drivers to determine what and when things get asserted to the bus. Now what's left here between pin 2 and pin 9 are 8 bits of input data, and then from pin 12 through pin 19 are 8 bits of output data. And that really is an implementation of a register. It's not very fancy. It's not that difficult to do. Where all the challenge comes in is all the interfacing, all the ancillary functions that we're going to need to do with each of those. So what I'm doing now is I'm bringing 8 bits up off the output. Straighten that pin out a little bit. 8 bits up off the output and placing them in the row right above it on the next breadboard. And the reason I'm doing that is I'm going to actually want to see what the contents of the register is. And I'm alternating up one, down one, up one, down one, just because these hookup wires, the black piece here that you grab onto, they are just a little bit too fat to stack them side by side all the way across, so I have to alternate a little bit. Pardon me. Now, I've got this, you've seen it before, it's the 1 red, 1 yellow, and 8 green LEDs, and I'm going to use the 8 green LEDs. I'll get that lined up here. And that then should allow me to see the data once I get some current limiting resistors tied to ground. Let me reach over my shoulder here and grab those. Okay. Now once again, I'm going to use 220 ohm resistors. I use those a lot for most LEDs going to ground when it's voltage on that actually is intended to light the LED. If I am going with a logic low or an off condition to indicate the LED is to be lit, I typically will go with 1000 ohm resistors so that I can protect the chip a little bit better, because the chip has to absorb the current for that output, for that to be on. So I've got a few of them here that are loose. I'm going to start with those. Several of them are already cut to length. Some of them are not. And I'm starting in the middle here, ground to the pin, because I am going to have to move side to side. So as I get farther and farther out, you'll see I'll have to kind of cut the corner here on some of these to get them to light. So those are my 2 pre-cut ones. Okay, so 8 LEDs. Well, I guess we'll start with the inputs here, and then we'll correct that shortly after that. And the challenge is going to be making sure that they all fit, all these wires fit. As I said before, these black barrels on these hookup wires are just wider than 0.1 inch, which makes it difficult to get them to line up. Now remember, pin 1 over here is output enable, and that's always going to be tied low, and we don't want to be messing with that. Okay, there's 8 lines. All right, so let's bring in power, and let's see what we've got here. Clock pulse is tied together, and I need to provide a positive or negative connection here. And let's just see, well, these are all off. Let's turn a couple of them on just to see if this is working the way we want it to. And the clock pulse, it's the low to high transition that latches that data. But I saw something different, and I don't know if you caught that on camera. So let me get a different value here. When I pulled out of high and switched to low, it did latch. And I wonder if that's the HCT difference versus the LS difference. If I change my inputs, and when I pulled it out of low and went to high, it latched. This is why I needed the test harness. All right, so let me grab some things. I'm going to create a quick test harness for this. Which means I need to grab a few things from my supply cabinet here. Breadboard. Okay. So I'm going to start with this breadboard here. This is one of the smaller busboard breadboards. And you saw these in a prior video when I was showing these off. These are the dip switches that will sit into a breadboard. I'm just noticing this breadboard. I don't know if you can see it, but it looks like something got really hot here and melted. I'm going to bypass that one. Save that for a rainy day. And I'm going to use this one instead. Anyway, these dip switches I got while we were doing some... I was doing some voiceover work, and I showed them. I'm going to pop them down here. And I need to... I hope I'm doing this right. I need 16 of them, 16 switches. And what I'm curious about is when things are up and when things are down, what is actually connected. All right, so I'm going to connect these to 5 volts down here. And I'm only going to do 8 for the moment, because I only have 8 that I'm testing up there. Okay. Then up here, I want to grab 1000 ohm resistors and use those as pull downs. I've got a few of them that are cut, so I want to try to use those first. Alright, so on this side I'm going to pull down. And yes, I have my own OCD on these. They have to be facing the right way. And I don't know why they put those gaps in there. If anybody has any idea, I'd love to know what the real purpose of skipping, leaving these solid here in the power rails. Alright, so that said, that now leaves me the ability to bring this and plug into that one, this and plug into this one, and again I'm going to alternate every other one. And that has a pull down resistor pulling the signal naturally towards 0 volts. And then when the switches are turned on, such as the most significant bit up here, the switch is turned on, then that should be connected to the 5 volt rail, meaning that it's a positive. And that is not behaving the way I want it to. Oh. I moved output enable, so I have something wrong here. I put them all in a row and forgot the gap in between the switches. So that left one line floating, which is not good. Alright. That's not doing what it's supposed to be doing. So perhaps with everything off, okay, that is not right. All right, let me grab. I'm going to bring the clock in here too. God, I hope that was on screen. I'm going to bring the clock in here too. And now I should have a clock working as well. And I'm going to grab a clock signal rather than this. So my clock output should be here. So it's the top 2 bits that aren't lit, and I have the bottom 2 bits here. Alright, so that explains that. So let's move this up here and get the extra bits. I just wired that incorrectly. Okay, so that solves that problem. Now, the question then becomes, if I switch one of these so that it is pulled high, okay, that's not working the way I want it to. Move to voltage. And grab a pin here. I'm going to stick this in ground so that I can probe there. Okay. But that is not as low as I want it to be. So that is not within the TTL or the CMOS low signal. I don't believe. 0.69, 0.7 volts. Okay, let's straighten me out here. I am not dealing with CMOS signal voltages. I'm dealing with TTL signal voltages. And 0.7 is definitely above the maximum voltage for a low TTL signal. So that's in that transition range. The second inaccuracy here is I start leafing through the 74 HCT 574 datasheet in order to try to find the proper electrical characteristics. Well, it's TTL compatible, so I pull up now for you the 74 LS 574 output voltages, and on the screen the maximum output for a low signal is definitely 0.5 volts. So in my infinite wisdom here, I went back to working on the breadboards, but didn't manage to switch the camera back from capturing my screen to capturing my work on the breadboards. So in that time, what I did identify is that this little test harness board is not hooked up to power and ground. So let me go back and redo that. I will hook that up to power and ground. Now, the reality of the situation is it didn't change anything. I am still getting some odd behavior. And it basically boils down to my clock pulse is not going anywhere. And so I dug out, where did I put it? I dug out my logic probe, and I'm going to hook this into power and ground. And I should be able to probe here. Well, I guess that helps if I flip the switch to have it go to the automatic clock versus the manual clock. So the manual clock pulses here. So that's working right, and I see I've got a value latched, and I've got it latched in the right spot. So apparently I have not had enough coffee. It's still morning here. So let's put an alternating bit of ones and alternating pattern of ones and zeros. That latches beautifully, and you can see that if I switch such that the opposite pattern and then pulse the clock, and you see that that shows up. 1 1 0 1 0 1. Pulse the clock. Okay. That indicates that I don't have anything switched or flipped or what have you. So my clock is coming from the clock module. My data inputs are coming from here, 8 bits of them. I still need to get this worked out for 16 bits. And I probably should go ahead and do that now. So I'm going to do one of those fast forwards while I work on getting this cleaned up and wire it out to the full 16 bits. Wiring up the switches is really more of the same. The first thing to do is to connect each of the switches to 5 volts so that when the switch is on, it passes 5 volts on to the register. The second part of that is to connect the disconnected side, or the side that's connected to the register, to ground using a resistor so that the value is actually pulled down toward 0 when that switch is off. And doing this, the challenge is really that the switches are 4 per block, the power is 5 per block, each one has one row in between. Where the power is blocked out, you can't use it. The switch is just too wide to fit exactly side by side. So as a result, not everything lines up straight. And I'm okay with that. My OCD isn't quite that bad. Okay, so what you would have seen is me hook up all of the connections to 5 volts, all of the pull down resistors, and then as I pull the wires out of here, I move them over here, hooking up to the what will be the least significant bits here of the register so that I can program those. Now my intent is not to leave these here. I will end up creating some ribbon cable to connect those short little bits of ribbon cable to make it a little easier to just drop it into any bus connection. So I will get to those here in a little bit. In the meantime, let me get one more. I'm going to grab a jumper here so I can identify exactly where I'm going from and to. So here is the least significant bit output. which I want to take straight up to here. And then this will be the least significant bit, trying to line it up right, least significant bit displayed on the LEDs here. All right, let me get that wired up and the rest of this board cleaned up, and then we'll come back and talk about what's next. I'm reaching over to my spools of wire and just making cuts and then pulling them back, and then I'll strip them and cut them to size and then drop them into the right spot. So what I'm doing here is I'm measuring the length of the wire that I need and then cutting it to length, and then I trim off the excess wire so that they don't go trying to poke down through the bottom of the board. So that pinhole wasn't allowing me to push the pin in, and as I went to one of the hookup wires, the pre-made ones, it also wouldn't go in, and when I actually finally forced it in, I think I ended up bending the rail inside. So rather than question if that is actually going to cause me problems down the road, I am just going to bypass that particular pin and call it a day. Now the other thing I'm doing up here is I am working on the resistors, making sure that the leads are trimmed short so that the resistors sit down on the breadboard. And then of course I've added 8 additional LEDs that I need to add resistors for. Once again, these are 220 ohm resistors because the positive or voltage high condition is turning on the LED, not being a voltage low condition where I would then connect to 5 volts on the other side of the LED, and of course flip the diode around. Okay, some quick testing here. Yeah, that works beautifully. I'm happy with that. Now the challenge is going to be these 2 unused LEDs. I'm okay with that. For the moment, I may have to take a black marker and mark over the top of them just to have those not recognizable. Now the last 2 things to do here is, one, deal with power. Sort of 3 power connections I need to address, connecting back and forth. This probably should be connected back up here. And then I do want to deal with this by switching those over to ribbon cables. It'll have to be a 4 and 4 split on this end, and then 8 on that end, 4 and 4 split on this end, and 8 on that end. But I don't think that's going to be a deal breaker. Interestingly enough, I used the last of my red hookup wire here. I've got more. It's not a huge deal. I do maintain a little bit extra supplies just in case I need them. And you'll see me pull that out later. For now, I'm just hooking up power and ground on one side of the breadboard. Ultimately, I may end up doing it on both sides or having multiple paths across the board, as I talked about with the timer circuit. But I need something a little bit larger to do an objective test before I make that decision. Okay, quick test. Let's turn them all on, make sure they're all working the way that we want, and then turn them all off. Okay, very good. So now to worry about getting these bus connections done. Okay, I've zoomed out a little bit more for this part. I had to collect some supplies. I ran out of red wire, so I have that ready to go into my dispenser box. The build is shoved out of the way in this direction. And I have this 10 wire ribbon cable. And this is what I'm going to use to do my bus connections, but I don't need all 10 wires. I ordered 10 simply because if I ever needed that, it would be easier to throw 10 wires into a particular connection if it was required. But it's easy for me to strip this down into smaller. So if I need a 2-wire connection, I could pull 2 wires off and then leave 8 available. And then I have these pin headers. I managed to get these off of Amazon. And these are intended to be soldered onto a breadboard, but I have these females, and I did not pull any males out. But I have these 4-pin, let's see if I can get this in a spot where you can see it. Now this is 4-pin. I'll zoom in just a little bit more for this. 4 pins, there we go. You can see the 4 little lines there. I'm going to need 4 of these 4 pins for connecting up my ribbon cables, because those need to go next to the dip switches. And these are 8-pin. Yes, I need 2 of those for connecting to my bus side. Zooming back out here. So that takes care of that. And then I need to go find my pins, my male pins. So stand by. And there they are. Now these pins get crimped around the wire. I've got a short little bit of, I believe it's 9 wire. These get crimped around the wire, so each one individually separated. The pins then get pushed into the end here once the crimping is done, where the pins pop out. And so that allows me to do 8 connections very quickly. So for the 2 wires that I want to create, I am going to need 8 times 4, 32 pins. The process here is somewhat tedious. The first thing I need to do is separate each wire in the ribbon cable down to just pull it back about 1 inch to 1.5 inches. And then I need to strip about 1/16 of an inch off the end of each one of those wires. And then I have to get a pin situated in the crimping device, the crimping tool. That has to be situated in such a way that it is held in place, but not so tight that it's actually pre-crimping before you try to insert the wire. Then I need to insert the wire to the right depth, which is really only about 1/16 of an inch in where the stripped back insulation is about a 1/16 of an inch inside the pin. The rest of it will grip just fine and make contact. And then once all of that stripping is done, then and crimping is done, then I can go ahead and repeat the same thing on the other side and then hook up the housings by sliding them in. Okay, so bringing the build back into view here. If I drop 8 pins here, and then 4 pins here, I'll stick them in the middle, not right up next to the switches, and 4 pins there, where you can see that there is a 1-pin gap in between. I should now be able to set everything on and prove that I have everything wired up properly. I hit the clock and all of the lights come on. That is awesome. So again, as I said, it was a little bit longer than I wanted, but I couldn't have split it in half. Should be able to drag the board out a little bit and play with the testing down here. Since I've already made one cable, I will make this one at ludicrous speed. While I'm working on the second cable, James Sharman also produced a video on how to make, and he calls them DuPont cables. I'm not exactly certain where the name comes from. I've always called them ribbon cables. In any event, he's got an alternative video on how to make these, and I will link to that in the description. I suggest you go check out James's channel as well. He's pretty far along in his build, and he's got some great performance out of an 8-bit CPU. Okay, let's bring the build back in. And then I should be able to replace all of these with this connection right here. All the lows are good. All the highs look good. So this then becomes my bus connection between the two boards, allowing me to dial in basically my bus input into this register, and then the bus output right now is displayed on these LEDs. More to come on that. Before I move on, I want to look at decoupling capacitors for these two new ICs. I'll work on decoupling for the board itself in a later video once I get the whole build of the register complete. Sticky. Alright, so in effect, what I want to do is I want to go from the power pin to the ground pin. So I'm going to make a bend here. And I will make a bend here. And then this should be able to slot. I'm going to have to back that bend up a little bit. So straighten that back out and go back just a hair. So from the power pin to the ground pin, right on exactly. And that being as close as it can get to the actual pins themselves, because really they should be across the actual pins. These are as close as they can get to that, so that's probably the best I can do as far as decoupling is concerned on the breadboard itself. Now, those are the right length, and now it's just a matter of cutting the leads so that they are correct. And so you can see I have reduced the length of this section of the lead. Let's see here. That section of the lead, so that this can sit down right as close as possible right on top of the IC. Okay, and then I need to do the same over here. And all I'm doing is just literally clipping the leads to a more reasonable length. So back to power, back to ground. There we go. And those are seated. In the next video, we're going to add line drivers for the LED output. If you were paying attention, you realize that these are directly connected to the output, and I want to have those separated so that the LEDs are not on the same signal directly as the bus signal itself. We're going to have a conversation about how we want the clock cycle to go and at what point certain things are going to be asserted to the different buses. And so, of course, that's going to be a number of bus control line drivers indicating when values off the register can assert onto which bus. And then we've got some register control circuitry to build, dealing with loads and asserts. So loading values from the bus, asserting values back onto the bus. And we still have our clock items that are parked as well. We'll see you soon.